Bom dia a todos, bem-vindos ao nosso quinto encontro da série de palestras de introdução à engenharia de som. E hoje é um dia bastante especial, né? Hoje temos o dia do INAD e eu não vou falar muito mais sobre isso, porque eu vou deixar o especialista no assunto, o nosso representante nacional, o professor William, falar sobre isso. Will?
Oi, Bruno, obrigado pela introdução. É um prazer estar aqui com vocês para essa sessão, né? Obrigado pela inserção aí, a presença do Dani está por aí. Bom, gente, hoje é um dia especial, né? A gente tem o Dia Internacional de Conscientização sobre o Ruído, tá? Que é o INAD, então International Noise Awareness Day, tá? Que é um dia símbolo para a gente fazer uma reflexão sobre o som, a audição e os efeitos dele na nossa vida, tá? Então, esse ano, por causa da pandemia, a gente tem as atividades online, tá? E a gente tem uma série de materiais sendo divulgados, seja no Facebook, no site, mas o grande veículo, acho que hoje em dia, é o Instagram. Então, vocês estão convidados a ver o @inat.brasil. A gente tem diversos materiais de engenharia acústica, da fono, da saúde, tá? E todos os anos a gente tem um tema e um lema, tá? O lema desse ano é Proteja sua audição, proteja sua saúde, que tem a ver, acho que, com o momento que a gente está vivendo, tá? E vocês estão convidados, se quiserem, podem escrever em box, me escrever. A ideia é a gente juntar mesmo o pessoal da técnica, da saúde, para a gente falar sobre o som e os efeitos dele na nossa vida. Com isso, eu agradeço essa introdução. So, thank you very much. Graças. Bruno, você pode tocar aí, a bola está com você.
Ok, obrigado, Will. Eu estou aqui fazendo tendo que admitir gente, um monte de coisa ao mesmo tempo. Mas depois da apresentação do INAD do Will, importantíssimo, né? A gente com fone de ouvido o dia inteiro precisa realmente se cuidar. E hoje a gente vai ter, então, uma apresentação sobre técnicas de medição, né, especificamente usando sensores de intensidade, que são sondas que medem tanto pressão quanto velocidade de partícula. O Dani vai explicar melhor sobre isso. E quem vai falar, então, quem vai nos apresentar hoje, fazer a palestra de hoje, é o Dani Fernandez, que é CTO, ou seja, o chefe de tecnologia de uma empresa, já foi uma startup, né? Hoje já é uma empresa grande na Holanda, que é a Microflown, que foi a primeira empresa a desenvolver esse tipo de tecnologia e colocar no mercado. O Dani é espanhol, da região da Galícia, então os alunos que quiserem, ao fim, fazer perguntas em português, pode fazer, que a gente estava conversando que o galego é o portunhol original. E depois ele estudou em Vigo e depois fez o mestrado e doutorado em Southampton, né, no Institute of Sound and Vibration Research, e depois seguiu para Microflown, onde tem atuado desde então. Dani, thank you very much for accepting our invitation, and we are all very excited to hear what you have to tell us about your new sound measurement techniques.
Sure. Thank you very much for the kind invitation. It's for me a pleasure to be able to share our work and what we do with your students and with your audience. I hope that after today it is a bit more clear that the techniques that we can use nowadays for solving acoustic problems in industry, especially when it involves sound visualization and noise quantification. So before we go to the presentation, I would like to give a bit of background how I end up in acoustics, as Bruno suggested. So for me, as a student, I was very interested. I play music instruments and started like playing in a band. I wanted to know more, and that's why I enrolled telecommunication engineering, thinking that telecommunication engineering in sound and image could be towards what I wanted, but actually discovered that it was more in the direction of acoustics and physics, and I like it more than expected. And I needed to know more, understand better, and that's why I went to Southampton and also with the mindset of I want to know more about room acoustics because I really like speakers and sound and music. But then I discovered the whole new world, a lot of different applications and what you can do with sound, and many different problems and aspects that can be solved in our daily lives with the help of acoustics and sound and vibration. So after completing the studies, now I'm continuously trying to develop new measurement techniques to make everybody's life easier. Like we develop the tools that the engineers use for improving their products, so the products are quieter and we all have a more comfortable life. Because yeah, nowadays you buy a washing machine and you check not only if the clothes are well clean, you also check out the dB label, how many dBs, how noisy is this machine. So we need, acousticians are needed in society, especially nowadays, and a good acoustician needs some good tools. So I will move on to the presentation and we can go through the content. I'll share my screen. Can you see the slides now?
Yes, we can.
All right, so I'll continue. So the motivation for this presentation is to introduce to the tools that we have today for solving acoustic problems. And we started, for more than 100 years, we have been developing different solutions to particular problems, like in the case of the beginning of the last century, they thought this could be both fast. Oh, can you hear me now?
Yes.
Hello?
Yes.
Oh, okay. Okay. So you couldn't hear me before, I guess.
No, we could.
Oh, all right. All right.
Mm-hmm.
So the motivation for this presentation is to give you an overview of the techniques and the tools that we have nowadays for solving acoustic problems. And this has been a constant problem for many years. And for example, we can see here at the beginning of the last century, they already started to making some tools that they thought that were not only useful, but probably fashionable. But nowadays we still have problems, although we have many time to improve upon what we use. But especially in environments where there's high background noise, like factory or industrial floors, and for solving problems of low frequency, it is a struggle normally to detect where the noise is coming from and what is the principal element that we have to modify to improve the acoustic problem. So particle velocity sensor offer a unique perspective because we can measure something that it is an alternative to the traditional pressure microphones that, depending on the conditions, can be very useful. So since 1994, when the sensor was invented until today, the technology has grown and developed along. The presentation will be split into 6 blocks. First, I will give an introduction to the microphone technologies and the microphone holding. Then I'll describe the particle velocity sensor, how the transducer work. Then we will move on into 4 different kind of technology to visualize and quantify sound, starting by the most simple of all, like listen and analyze directly with your brain. Then go into 2D pictures or acoustic imaging. Then we will move to 3D sound visualization, so full control of the acoustic field. And at the end, near field acoustic holography and near field sound visualization using arrays for non-stationary problems. So here you see the location of Microflown, the headquarters. We are on a couple of floors of this building in Arnhem. And the company started already more than 25 years ago when the invention, the triggering element was the invention of the microflown sensor by Hans Elias de Bree. By that time, they did not really know exactly all the potential or the use cases of these type of sensors. So they were finding along the way, after funding microflown technologies together with Alex Kurz, how this new transducer, new sensor solution could be industrialized and brought to the industrial market. At the beginning, the first applications went into the direction of the automotive. And once it was proven the usability, how can we make use of this device? How can we prove that actually we measure particle velocity and that we calibrate the sensor to measure this acoustic quantity? The company experienced a rapid growth and getting more and more bigger size. So in 2010, there was a big important landmark for the history of microflown, because we started to introduce not only sensors, but also whole solutions. So hardware and software sold together to solve a specific problem or application. And that's the case, for example, for the Scan and Pen 2D, where you can have one sensor, one software, one camera, and get an acoustic picture. Given the potential of the sensor and the range of applications we're expanding, also in 2011, we founded the military site, Avisa, and later on the maritime for underwater or near water applications. In the latest year, we also expanded to Scan and Pen 3D, so full control of the acoustic field. And the most recent event or big landmark was the introduction of Voyager, the full portable measuring solution. So not only some simple software and hardware, but also the electronics and all the components designed by us. And at the moment in the holding, we are more than 40 full-time employees. But the company, as I said, is divided in 3 main blocks: microflown technologies, focus on civil applications; microflown Avisa for more military or related to safety applications; and microflown maritime. So as you can see, the range of applications or the range of usage for our technology is quite broad. And today, today's presentation will be mostly focused on microflown technologies applications. Our company has an international sales network all around the world, and the headquarters is in the Netherlands, in Arnhem. Here we develop all both hardware and software that we sell, but we have partners worldwide that we closely collaborate with, and they distribute or demonstrate our technology, and we could travel with them for specific consultancy services for the customers that requires it. The markets of the technology go from automotive, maybe the majority of the market share, followed by appliance and electronics, heavy industry, aerospace. Now we're moving towards quality control as well, building acoustics, environmental and educational research. We work with many brands that you probably know, especially in the automotive sector, but also more and more we are growing into the appliance and electronics, since, as I said before, people care a lot about the performance of their device and how quiet they are. So we have broad spectra of knowledge on the type of problems that the industry have at the moment. And we will start focusing on how to solve it with different technology. And before we move on to the specific systems, I would like to introduce a bit more about the particle velocity sensor and what does it mean and how do we measure it. So that's why we move to the next section. So if we look at the fundamental quantities of acoustics, we can separate the energy or the energy interchange between sound pressure and particle velocity in the same way that in terms of energy, we will have potential energy and kinetic energy. So if we visualize what does it mean, these two quantities, we can have here in the upper side like an impedance wave tube, a piston that is moving and is compressing the air particles, getting them close together. So when the particles are close to each other, they experience a force because they want to be as equally spread as possible. So that force is directly related to the sound pressure. It is how much pressure do I experience at one particular point in space. So when the piston moves, compress, and then that compression travels through the waveguide, and but this is a local, like the particles only oscillate locally and not travel through the tube. So when we look at the velocity of one particular particle and a point in space, we will see that these local oscillations going away from the resting position will have some moments where the velocity is higher and the velocity is lower. And that's particle velocity. It is not only how much force do I experience, it is more related to the speed, local speed of the particle, but it also has a direction associated to it. So it will tell you where the force is coming from or where the cause of the problem it is, where the sound wave is coming from. So that's a key aspect, as we will see, information that you don't traditionally capture with the sound pressure. We can quantify, but also we can tell direction for one particular point. And how do we do that? The microflown sensor is based on a MEMS principle, microelectromechanical sensors, and it's not a moving piston. We work with two hot wires that are close to each other, and when the wavefront comes, there will be a heat interchange between the wire and the fluid. So the particles will heat up a little bit and cool down the wire. And when the wavefront keeps traveling to the second wire, there will be a second interchange of heat, but not as much as the first one, because the first wire heat up the particles. So the second wire will cool down less. And therefore, there will be a difference in resistance in the two wires because they have different temperature. So if we pass the same voltage through two different resistors, we can actually measure the difference between them, and that is proportional to acoustic particle velocity. But going to the practical side of things, what can we do with this particle velocity, or what can we expect in a practical scenario when we have a normal microphone and a particle velocity sensor? So if we are approaching a vibrating surface, for example, we will see that the pressure linearly goes up as we get closer, but the velocity level rises much faster when we get very close to the surface. So if you are farther away in terms of dB, we will measure the same, like let's say 80 dBs, but the closer we go, we can get like 10 or 20 dBs more than the pressure if we are in front of a excitation source. In the opposite effect, like if we are, for example, in a room, there is noise everywhere because there's a noisy machine in the middle of the room. If we get closer and closer to the floor or to a wall that is not vibrating, in terms of pressure, we will see a local increase because the incoming and reflected waves, they add up. There is a scalar quantity, and everything locally will be amplified by the reflector. But in terms of particle velocity, there is direction to it. So the incoming wave has positive phase, the reflective negative phase, and the more closer you get to the reflector, the less velocity you have. So in practice, if you go close to a noisy machine in a noisy environment, you will have very high noise. If you go close to a quiet machine or a high impedance machine, velocity will go much lower. And besides that, the directivity is a figure of fate for particle velocity elements. So for low frequencies or high frequencies, we will have the same capabilities to aim towards certain direction and reject the noise coming from other directions. So in practice, what we have is higher signal to noise ratio to identify more accurately the location of noise emission. And we are less susceptible to background noise because of the directivity and the near field effects. Depending on the application, we can choose to mount the sensor in different probes. We have one-channel probes, so the velocity comes along, and then we can choose 0 or 90 degrees orientation. If we want to measure pressure with velocity as we will see later, it is very interesting because then we can get the sound intensity, and depending on the application, if it's very tiny, like a miniature device, then we will need a PU match, for example. But if it's a bigger size or a more harsh environment, we will have other type of probes that are more suitable. And if we want to have the full velocity vector, then we will need 3 orthogonal velocity sensors together with a pressure microphone for a 3D acoustic vector sensor or 3D sound intensity probe, and that will be the USP probe. So here we have to give you an idea on how we perceive the difference in a practical example. I will play a video now with a booster. It's an automotive component that moves the air from the front part of the cabin to the rear part of the cabin. It has 2 fans, and we will hear how the sound pressure and particle velocity sound near this device. All right. So moving on to the first system, now we have described the technology, the sensing technology, and how we capture acoustic particle velocity. And the first and most simple way to solve an acoustic problem is directly by listening to the different acoustic quantities, so pressure and particle velocity. We have our portable data acquisition and recording device, analyzer device, which is the Voyager. And here we can directly record measurements, connect the probe, select the channel we want to listen to, filter certain frequency band of interest that we want to assess or where the noise is coming from, and even attach additional sensors if we need, for example, relative phase or relative transfer function measurements. And here in this video, we can see how we measure a device with the purpose of ranking. So we just have to scan around the surface of interest, and then in the software later import that information. So then we can say, okay, this machine have left side, top side, rear side, assign the measurement data, and then we can obtain some table to rank which part of the machine is more noisy and how many dBs more or less in terms of sound power we have for certain frequency regions. So it can be very easy and straightforward to make a sound power ranking just by using this kind of platform. And one example that we have for solving an industrial problem with this kind of approach, this will be, in this case, a metal pipe company that have a very large machine. It was like 12 or 15 meters long, and they have a very big factory floor, so like the reverberation time was very long. They wanted to see which part of the machine to improve, how to change, how to reduce the emitted noise. So we just measure scanning around different parts of the machine, imported the data, and directly obtained a ranking that said that in this case, this machine that cuts metal pipes had an issue in the intake system. So when the machine load the pipes into the cutting section, there was metal, like a lot of metal hitting each other and producing a lot of noise. So they will have to create a cabinet around that area if they want to reduce. And it was like more than 4 dBs higher than anything else. So it would be effective to apply a noise treatment on that area. And that's what they did. So at the end, they achieve, it took us like 1 hour to do all the measurements and the processing. And in that time, they could find the solution to the problem kind of straightforward. So it is quite effective. In another case, this is more for the investigation on electric vehicles, for motor detection. They have limited, especially the new companies, they have limited access to environments which like semi-anechoic chambers where they can operate their motors because their time availability is really low. So for prototypes, it's easier for them to evaluate things into a more rough lab, not acoustically treated. So it is very important to have very good signal-to-noise ratio for detecting parts of the motor that produce tonal excitation. So in this case, we can see here, if we compare the pressure or velocity that we capture at different areas, the signal-to-noise ratio is much higher. So that allows to identify the weakest spots and apply local treatment and evaluate again the modification and improve the machine kind of quickly. But this straightforward way to solve problems is not the only one, and especially when you need to communicate to other people, that like managers or people above the engineers, people really like pictures, so they want to see with colors and understand what is going on or what is causing the problem. And for that, we have for stationary sound fields, the solution is Scan and Paint 2D. So Scan and Paint is an acoustic imaging solution that just with one probe and one camera, we can produce these kind of pictures that can be applied. The same system can be used for evaluating tiny devices like a hearing aid, as we see here. Or if we go farther away and we put a bigger marker in the probe, we can evaluate like very large turbo compressors or piping machinery or even cars. So it's very versatile solution that for stationary problems can be very, very efficient. And here we see a video on how it works. In this case, we are scanning with 2 markers in the probe, and the program automatically detects the position. So mixing the signals that we capture with the position, we can directly discretize the sound field into areas and be able to localize the excitation points for different areas. For an application case of this type, here we have a study or a consultancy we did together with Bentley. In this case, they were interested on reducing the acoustic treatment that they typically apply in their body, in their car body. They wanted to make it as light as possible, but also keeping the acoustic performance within their targets. So what we did is evaluate different surfaces of the whole car and find out for different parts of the car, we can see resonance panels, apply certain treatment directly to the panel, just stick thermoacoustic parts into it, and then they reduce the vibration and effectively reduce the noise into the cabin. So by assessing this vehicle in several stages, we managed to reduce by 15% the total cost of the acoustic treatment. So it was quite successful. And we made a publication and they kept on using the same technique, and they have told us that also they like some cars that came later, they achieve even 30% cost reduction of the whole body package and weight reduction. So it is a nice way to use velocity to identify key vibration points and optimize the acoustic treatment needed to make the comfort of the passengers better. With the same system, also, we can evaluate noise from compressor of big machinery. Here, there was a particular problem that Rolls-Royce needed to solve because there was a customer that bought a turbo compressor for their factory. A third-party company installed the piping system. And when the customers were on site with everything ready, they detected that there was like the noise levels were way above the health and safety regulations allowed for the people that had to work on that environment. So Rolls-Royce blamed the piping company blamed Rolls-Royce, and nobody wanted to, everybody said that everybody was doing everything according to specs, so it was not their fault. And after calling a couple of companies and not being able to solve this issue, they end up calling us. And after performing like a quick measurement, less than half an hour, scan and pen results, we can directly see that there is a middle section pipe that was way higher than anything else, in this case more than 20 dBs. So directly the problem was spotted. And when they dismounted this middle section, they found out that there was a restrainer, like kind of a metal grill that prevents particles to go into the turbo compressor that was not welded properly. So it was rattling inside and creating all the noise. So they successfully replaced this grill, this restrainer, and reduced the overall noise more than 10 dB in the whole factory floor. So it was they were very happy. So this is for 2D, and when we want to evaluate sound emission and spot different locations, can be very effective to have just the color picture. But not all the problems can be solved with such approach. Sometimes we also need to know how the cabin interior or how the environment where the acoustic field is interacts with the produced sound, and therefore we need 3D information about it. And for that, we have expanded the scan and pen 2D to the 3D dimensions with using, instead of a 1D probe, a 3D probe. So one channel for the pressure and 3 orthogonal velocities. But we also need 3D positioning in space, and for that we use a stereoscopic camera that is able to track both position and orientation of the sensor. And once again, combining the signals with the position, where we can create the acoustic, we can capture the acoustic field in all 3D. So here I have a video presenting how to measure and calculate all the process. As you can see, we can capture a lot of information, so it is important to have a good understanding of the problem to be able to, like, you have all the information available. So if you know what is causing this, for example, vorticity or strange problems with the cavity, then you can troubleshoot and evaluate if your measure is effective. And one example of the use of this technology is, for example, here for audio system verification. So when you mount a new speaker system in a car, they want to verify that the speaker placement they chose and the type of speakers they have into the door and the frame of the car, that is giving the passengers the correct response, and spatial distribution. And for that, we can map how the sound propagates from the drivers itself to the passengers in the whole cabin. So we see, for example, in this case, from 50 Hertz to 3 kilohertz, it is clear that the mid-low buffer that it is at the door, it is radiating directly to the driver, British driver in this case. And if we go for the mid-high frequencies or for the high frequencies, 3 to 10 kilohertz, there is a tweeter mounted into the A pillar, and that we can see also radiation going from there to the passenger. But there is some frequencies that the person that was sitting there experienced discomfort. In this case, they reported there was the level difference between left ear and the right ear was really high, more than 10 dB. And when we measure what was happening in that particular car, we could spot a cavity resonance just at the driver ear. So around 750 or 800 hertz, we see a cavity mode that have a node in the left ear area. So effectively, that will increase the sound on one ear compared to the other, and that is not the best experience that the user can have. And therefore, they had to apply some treatment or change different position or make the structure a bit different to mitigate this strong modal component. Different vehicle, in this case, it was an airplane. And we did an investigation together with Airbus to reduce noise inside the cabin. And they wanted to, it is hard to see, but it was like a big section of the plane. So we needed to investigate for different frequency regions what to improve or which areas should be treated more carefully. Here we see, for example, the extraction grills, like the ones that suck the air that is in the cabin interior towards the piping system. That is cooled down and clean, and then is again pushed into the cabin through the ceiling grill. In this case, mid-high frequency ceiling grill was the dominant source, but there were also some pipes that have T connections that at mid, like high frequencies, they were resonating, so they created also quite some noisy tonal components that were really unpleasant. So after this investigation, we could spot also resonance in the fans that are, all these fans that move the air, they were in this plane position underneath the floor. So for some certain areas, we could also say that they were there. So some fans were well isolated, but other ones not. Like in this case, in the rear section of the plane, we could spot some tonal components caused by those. So applying additional treatment, they could reduce the noise in the cabin. And yes, my last section of the presentation, we have seen how to measure directly and listen, understand, or visualize the acoustic signals. Also get pictures 2D and also 3D. And now I want to show an example, a different one for when you have a problem that is non-stationary. So for example, an engine that is running up, or we have an actuator that's moving small parts, and there is a cycle that happens, and we want to evaluate at each moment of time where the noise source is. Then we need to use acoustic arrays. In our case, we have arrays that consist of PU probes, so one pressure, one particle velocity, and that allow us to calculate with near field acousticography, they render the sound field near the radiation surface. Depending on the purpose, we can spread the sensors into an arbitrary configuration around the noise of the source of interest, or we can have a predefined grid with certain spacing or optimized for the post-processing method that we are going to apply. But the overall picture, what we will get, it is like an image render of the sound field, and we can see for different frequency range how the dominant sources interchange. So for particular problems, we can study if we want to evaluate certain regime of operation, we can study in the frequency domain, or if there is rotating machinery in the order domain, and evaluate and quantify for different stages of the operation what is the most problematic part. In this case here, we have a window wiper actuator, the one that moves the wipers in the car, and they wanted to optimize the behavior and which of the motors are the most noisy during the cycle. Here we have another example where we use our technology to evaluate modal behavior on a plate. We see in a red circle the point of impact. So behind this metal plate, they will have a hammer and hit with the hammer. And even though there's very low frequency, 40 to 60 hertz, we can see the first mode very clearly on this plate, as well as the second mode, see a very smooth pattern over the whole plate. So in this case, they were studying how to apply different multi-layer treatments to the plate and how that will affect the modal behavior. And that can be easily evaluated with this kind of technology. So I'm just coming along to the end of my presentation. Today, we have seen 4 different types of systems for sound localization, 4 different solutions, from the most simple listening and analysis device, which is the Voyager, to a 2D scan and paint that create acoustic pictures, mixing color with an image of the area, a full 3D sound mapping solution, and also near field acoustic arrays that allow us to evaluate problems in real time, assessing how the sound field change over time. I hope that you enjoy the presentation, and I'm happy to answer your question. Thank you very much for listening.
Dani, thank you very much. I'm pretty sure everybody enjoyed it. It was super interesting. So if somebody saying it was incredible class when you were explaining about sound field. So yes, pretty sure people enjoyed and grateful for that. And we do have some questions. So I will go and ask if Alexandre wants to start. Otherwise, we can read the question he posted. Alexandre, se você quer fazer a pergunta? Alexandre Piscina.
Doesn't have a microphone.
Ah, no microphone. Okay.
Can read the question.
Yeah. So Alexandre was asking, considering that cooling, he's talking about the particle velocity sensor that works with a difference in temperature. How does that work when you have a mean flow? I'm thinking he's asking what happens if you have a wind going through it. How does the probe deals with it?
Then things become complicated. As you can imagine, what we need is ideally to have stable conditions of temperature, because the sound wave will move the heat, and that's what we perceive. So if there is a DC flow, that can affect how the sensor perceives acoustic particle velocity. To prevent that from being an issue, we have metal mesh protected in all the sensors, and that allows us to measure up to 1 meter per second with no disturbance. But 1 meter per second is not much. So if in practical applications where there is some mean flow related, we have windscreen porous media surrounding the sensor, and that actually just slow down the flow, the airflow. So when they reach the sensor, the effect is minimal. So it is indeed one of the challenges of this technology that we have to ensure that there no DC flow directly attacking the sensor, because with the output will not be acoustic response, it will be voltage disturbance.
Mm-hmm. Yeah, cool. There is also a question from João Panhan. João, do you have a microphone? You want to go ahead and ask?
So first and foremost, are you hearing me? Are you hearing what I'm saying?
Yes.
Okay. So first and foremost, thank you for the lecture. It was very nice to hear about those things. And my question is, how do you deal with the effect of turbulence on your measures when the speed or the pressure of the air particles gets very high?
The air turbulence, you mean?
Yeah, yeah. The effect of turbulence measure.
Yeah, actually, we do not measure much when there is air pressure turbulence directly attacking the sensor. So what we need, for example, we have some measurements for wind turbines outdoors, and in that case, we need bigger windscreens that protect the sensor against this type of phenomena. So depending on the application, we will have to attach accessories to the sensor to make it be able to cope with those problems.
Okay, thank you.
You see, the guys already noticed the shortcomings and went straight to that. But
I mean, it's not a problem that cannot be solved. You just have to beforehand be careful, and that's it.
to know the limits, right? To know how things work and be prepared.
Yeah.
Well, when you were discussing about the signal to noise ratio, you meant that it's good. You have a better signal to noise ratio if you're close to the source, right? To the sound source.
That's correct. Yeah.
If I'm far away, do I still have any other advantages of using the probe besides measuring intensity, of course?
Directivity is the only other thing, but the near field effects only happen in the near field. So when you're acoustically far, then the thing remaining is the directivity. That's broadband. But ideally, for example, if you have a point source and you are, I don't know, 1 meter away in the outside, if you check the dB level of pressure and velocity, if you are aiming to the source, it would be the same. So
and then, at that, once it gets to a point that you're close to a plane wave, then it would be the same.
Yeah, exactly. And then also pressure, velocity, and intensity, they will be the same level, the three of them.
Well, not the same level because you still have the impedance too.
No, the same level because the dB level, the reference has the Rossi scaling factor. Eric,
you
I do have a question, and it's not related to impedance, surprisingly. Yeah, I've been at Microflown for a short period. I see now that instead of pictures of people, you have already meshes, 3D meshes. That's very much fancier. I would like to have a mesh of myself, by the way, but okay.
Actually, the student that was in the video is also from Brazil.
Yeah, it's Mateus, yes. Thales was in the video as well.
We realize you like Brazilian models, right?
Yeah, we like Brazilian models.
The ones that don't know, Microflown has 4 Brazilians now at the team, right? Or 3 and 1.
3 plus 1 coming, yeah.
1 coming.
So the question is about the near field array.
Yeah.
So how I don't know if you can say this, but how exactly do you use the information on the particle velocity to do the holography? Because if you are using some sort of basis functions like plane waves or spherical waves, then the velocity is related to pressure by Euler's equation.
Yeah.
And essentially the coefficients are the same for both of them. So how do you use the particle velocity to give extra information about the holographic process?
Actually, if you look, really in detail between the pressure and velocity from the starting point to the reconstruction side, if you reconstruct pressure to pressure is kind of straightforward, the basic functions to propagate. From velocity to velocity, the same, but the cross, it can be tricky depending on the signal to noise ratio and the base functions you use. So what we use for the acoustic camera is the pressure to pressure, velocity to velocity reconstructions to make it as robust as possible. So in principle, you can use pressure for reconstructing velocity, but you are exposed to problems when you have not very good signal to noise ratio, especially in situ for real measurements, because there is other machinery around and you are making assumptions like, I go from my measurement plane to the surface and there's nothing else, but maybe there is a lot of stuff around. So that could make the model produce some anomalous answer, and that will be much mitigated by using all these quantities.
Thanks. Great talk, by the way. I enjoyed it a lot to see everything.
Thank you. Thank you.
May I ask something?
Oh, I was going to say, Will, do you want to say something?
Yes. Yeah. Well, I think maybe we both like to work with arrays, but we know the problems to work with arrays, low frequencies. So when I was there visiting you, I was amazed by how you can measure down to low frequencies. So just to elaborate concerning the systems you showed us today, so down to what frequency is it possible to measure or to do measurements?
At the moment, most probes come calibrated within the 20 hertz to 10 kilohertz range, and anything that is within the calibration area, it can be measured, no problem. So I would say, as you can saw in the example, we apply holography with 40 to 50 hertz, and you can see very nice mold shape. And I've done measurements in the range of 20 to 30 as well. So I'm confident to say that above 20 hertz, we can evaluate problems as long as you cover partially the source that emits the
and also creating the intensity maps.
Yeah.
That's quite nice.
Actually, we have a case study in the website about engine in a boat. They wanted to measure different conditions, and they measure, I think, there's 25 hertz or something like that, comparing a different condition on boats, and then they have quite some good results. Nice. It was for the Spanish Army. No, not Army, Navy. And yeah, they made a publication about it. So yeah, in the above 20 hertz, absolutely should work.
And I recently saw that you have also included a pressure field calibration. Is that true for what kind of pressure or particle velocity sensor?
Both pressure and velocity. So we have introduced now, we are introducing for the new probes one adapter that you can connect to the in-field calibrator. So then you can perform the regular calibration, and then you can do a sensitivity update. So not the whole frequency response, but just an offset that goes up and down. But for field calibration, that's quite enough, I would say.
Okay, to set an offset, right?
Yeah, it's just like regular offset you have, and because the pattern of the velocity sensor, it is stable over time, quite stable. So every 2 years, we still recommend to send the sensors to reestablish this full calibration, but for day-to-day calibration, the field calibration is enough.
Great, thanks for the nice presentation. Congrats.
You're welcome.
Marcio, do you want to?
Yes, Dani, thanks a lot for your very nice talk. And I was curious to have an idea of how does the price of a probe compares to the price of a measurement microphone, and are there any ideas for using the particle velocity probe for audio applications, like sensing, for instance, the sound of a guitar or something like that?
Okay, regarding the price, I think I'm not sure if I can answer directly, because it depends on the territory.
Okay.
Our distributors have the pricing established for different areas, but I can tell that normally, if you compare a PU probe with a pressure microphone, it will be more expensive. But if you compare a sound intensity probe, a PP probe with our probe, then it would be kind of on the same range. So that's kind of more the focus that it should give. Since you get sound intensity, we are on that more towards that range than the pressure microphones. And about the acoustic recording for instruments, unfortunately, the sensitivity drops for higher frequencies. So if you see the natural response of the sensor, the higher you go, the less sensitive you are. So we compensate for that to be calibrated. So when the things make a lot of noise, that's not a problem. But for especially music on audio, you want to see like really, like it has to be very precise at mid-high frequencies because we are susceptible to it. So that is still a challenge to lower the noise floor at mid-high frequencies if we want to go into the audio industry.
Because the sound example you showed, they sounded really nice. And,
okay, thank you.
Better than the sound from the microphone. So
yeah, still,
that's probably because they were low pass, right?
No, I realize now that one of the videos you can still hear there's some high frequency noise in the velocity channel. So at least one of the videos was for sure raw time corrected signal. But it could be, yeah, for audio, people are quite picky. So far we haven't made it through successfully. We have to improve the sensing technology if we want to go that direction.
Okay. Yeah. Thank you.
You're welcome.
Dani, there is also a question from Victor. Victor, do you want to ask, or should I read it out loud?
Can you give us some book recommendation about particle velocity measurement? Where can I find more information for self-research? Yeah, I would say if you go to our website, in the resource section, we have books, we have publications, case studies. So there is plenty of information online that you can check. Depending on the topic that you find interesting, we have a whole ebook with chapters on different topics, or we have theses on, if you like, some visualization tools. That was my PhD thesis, so you can check. If you want to go more into cars, also like that. So there is quite some free material. But anyway, if you are interested about anything specific, you can also write us at info@microflown.com or me, Fernandez@microflown.com, and I can give you some good examples or literature to read on.
I think on a more general term, probably the book from Fahy would be a good starting point. Right?
Yeah, for if you want about sound intensity in general, the Fahy's book probably is the best, or Jacobsen book. I personally like it more. The Fundamental of Sound and Vibration.
Yeah, I think those are very good starting points.
Yeah.
If you want to get to know a bit more of sound intensity and sound in general, actually, but then going into intensity. So, as I said, the discussion goes goes very well, and it goes by fast. And we already reached 1 o'clock here, 6 o'clock at your time. Probably time to go home.
No problem.
So, if anybody else has a last question, we're happy to take it. Let's see. So they're talking about something else in the chat. So yes, Dani, thank you very much for the presentation. From what people have been writing on the chat, you probably noticed that they really enjoyed it, and it was really a great presentation, full of information, and not only nice examples from the industry, but really hard information in there. Thank you very much. And,
glad to hear that, and thank you so much for the opportunity.
Yes.
I think Eric has a question.
Sorry, I think it was supposed to be like applauding, not raising hands. Sorry.
No problem.
So that one.
we are still learning how to live on this virtual life that we're now that's been imposed to us. There is one question coming at the chat here. Ms. Denok, he's asking if there is something you could share about underwater acoustics and how do you use the probe for underwater acoustics?
Unfortunately, there is not much we can share because it's still the probe at a prototype stage. There is some public information, but it's mostly in the research phase. So for underwater, there's not much material available.
Have to wait.
Yeah, we have to wait.
Can I have make a last question?
Yes,
sure.
Go.
Dani, is there research and development department at Microflown, or is it mostly done also in contact with the universities?
Both. We have our R&D department, and we closely collaborate with universities. As you can see, we like Brazilian researchers, and we have been gathering students from Brazil in general, but also we have close collaboration with other universities in the US or China or Turkey, Germany, Spain. So we constantly try to keep up with the latest research and push in the different directions, getting to know better the boundaries of our technology together with the academics.
Mm-hmm.
Yeah.
Okay. So, Dani, once again, and for the last time, thank you very much.
Thank you.
Great presentation. And next week, we meet again at Wednesday, 12 o'clock Brazilian time. Tchau, tchau, pessoal.
Bye-bye.
Bye-bye. Thank you.
Thanks, Dani.
Obrigado, Dani.
Obrigado.
Gracias.
Gracias.
De nada.
Na Galícia, não sei como se diz. Obrigado.
Gracias.
Graças.
Gracias.
Obrigado.